I'm going to be talking about work that we're doing in my group at Columbia University to develop forecasts of the growth and the spread of infectious diseases. I'm mostly going to focus on influenza, which has been the case in point that we have worked on. And before I start, I want to define the context in with which I refer to forecasting. So I think in the larger picture of infectious disease outbreak preparedness, there are a number of spheres that you can think about for being prepared for the emergence or the growth or the spread, the geographic movement of diseases, pathogens. On the upper left, you can see this is sort of divided into three little groups right here, but there's a surveillance and emergence detection, and that's the actual discovery portion to try to see it. And to actually have systems in place that allow us to be aware of what's actually in circulation and what might actually emerge, and if it does emerge, to detect it as early as possible. On the upper right is the idea of risk mapping, okay? And that would be something more along the lines of using cartographic methods or ecological niche modelings, or a number of approaches people use to map risk potential and to paint what areas, due to the ecology, environmental disruption, human interactions, the presence of certain agents, certain zoonotic reservoirs, et cetera, that you might see the spillover of certain types of diseases, be it a coronavirus or a hemorrhagic fever or something of that sort. The last one down here is the idea of forecasting outbreak growth and spread. And that's the one that I'm going to focus on right here. This is what we do in my group, and this is once a pathogen has actually emerged, once it's in circulation, in particular within a human population, because we're focusing on the human host, can we forecast the growth of it, the incidence levels in future weeks? So we're not looking to predict an event before it happens. We're actually looking to try to predict, once that something has emerged, how it's going to develop and the extent to which it's going to manifest and the spread that will take place. And I would argue that that upper level prediction, well, let me put it this way. If you were to try to actually look at the idea of predicting an emergence event, like predicting that Ebola was going to spill over into human hosts in 2014, that's a very, very challenging problem. And that's something that I don't think there's really any analog in any other system around that suggests that we're particularly good at it or that we're going to be capable of doing it soon. So for the type of forecasts that I'm talking about, like how much flu are we going to get over the course of the season once we begin to see it ramp up? How many cases are we going to see? When is it going to peak? I like to think of these forecasts as part of a continuum of information that we have at our disposal, an information stream, if you will. It starts in the past with observations, which tell us about how conditions have actually manifest. It continues into the present with something we call nowcasts, which are statistical estimations of what's going on in the very here and now in the absence of real-time information. It's sort of a stopgap measure for filling in the blanks because we do not get real-time surveillance in all instances, usually, really. And it goes to forecasts, which tell us something about what's going to happen in the future. Now, associated with all three of these measures of information, we have uncertainty bars. And as you can see, the way I've schemed it out, it tends to be the case that as you go from the past to the present to the future, the uncertainty increases. Okay? Now, that's not always the case. You can have very good forecasts where that gets really scrunched down, and you can have really lousy observations where you have very wide uncertainty bars around it. But I think any judicious use of any of this information in an informed manner has to account for that uncertainty associated with the piece of information in hand. And I would argue that it's the job of science and operational forecasting and the work that we do to try to shrink those error bars around it and increase the certainty we have around these pieces of information. So I'm going to cut ahead to the type of modeling and forecasting that we use. We use something that we borrowed from numerical weather prediction. This is not to say that it is weather-based forecasting. This is to say that we use the same dynamical inference framework that they use to generate weather forecasts, and we've applied it to disease systems. So when you look at something like this figure on the right, which shows influenza-like illness, syndromic surveillance for flu, for New York City over a period of a few years, you can see there's a lot of variability from year to year. The size of the outbreak differs, the timing is different, the duration of the outbreak, the overall attack rate. And this is a result of the fact that these outbreaks are nonlinear in their core dynamics. Because of that irregularity, you can't simply make a prediction using a dynamic model that describes, let's say, the propagation of a pathogen through a local population on its own. So the strategies that we borrowed is to construct, instead of just using a free dynamic model, to combine it with Bayesian inference methodologies. So 3 ingredients are required to do this. We need some sort of observationally validated model of influenza transmission dynamics, something that's capable in free simulation of representing something that's characteristic of the types of outbreaks that we see for a particular disease. We need real-time estimates, or as close to real-time as we can get, of the system itself. In the case of weather, this would be satellites and ocean buoys and ground-based stations and plane flights and balloon soundings. For us, it's something along the lines of influenza incidence, infection rates, or some other measure of disease incidence that we can get a hold of in near real time. The last ingredient that we need is something to combine these two. What we're looking to do is we're looking to combine the real-time estimations in a way that optimally informs the model in an iterative fashion, and then we want to use that optimized model to make a forecast. And to do that, we use something that in weather prediction and in the geosciences they refer to as data assimilation methods. Statisticians might call it a sequential Monte Carlo method. They're these Bayesian inference methodologies that you can couple a dynamic system with and use it for that optimization procedure. So I'll give you a lowdown on one of the basic systems we had. We had a humidity-forced compartmental model, very simple model that describes influenza propagation through a local population. It's just a 2-variable nonlinear oscillator, couples a couple ordinary differential equations. It happens to have an environmental component. That's not critical to it, but it does slightly improve the skill of the forecast, it turns out. But this thing in free simulation is capable of actually generating an outbreak that's consistent with the dynamics that you might see of an outbreak in Seattle in a given season. All right? For the second ingredient, we're going to need some sort of measure of incidence of influenza. So for municipal forecasting, we often try to use something a little bit more specific than influenza-like illness, which is a diagnostic measure. We tend to take that measure of ILI, that estimate of it, which might be done through proxy estimation or nowcasting, or it might be actually directly measured and available from a municipality, but we multiply it by influenza-positive test proportions. By multiplying these two together and making it something that we term ILI plus, we're filtering out a lot of the other signal associated with other respiratory virus infections that can also produce similar symptoms. So ILI itself is very nonspecific. It has rhinovirus, adenovirus, parainfluenzas in there, human metapneumovirus. By multiplying it by the fraction of people who actually were tested, who tested positive for flu, we filter at least that component of it out, and we get something that's a truer estimate of influenza. And you can see that in this plot right here, where the green is ILI plus and the blue is ILI, again for New York City over a period of time. And you can see, particular in those years 2005, 6, and 7, it's cutting off that early outbreak signal there in particular, and that's associated probably with rhinovirus. So the last ingredient we need are these data assimilation methods. They are these recursive iterative filtering algorithms. They go by a lot of names. There are a lot of versions of them: particle filtering, Kalman filtering, lots of different types of these exist. Variational methods is another form of it all. They're used in a lot of different disciplines, lots for engineering, design, and optimization, and certainly for numerical weather prediction. And we're going to apply it here to this compartmental model that represents influenza. So why are we doing this? We do this because there is a lot of error in the system that we're trying to forecast and a lot of error in the model system that we're trying to use to represent it, okay? And the errors manifest in a number of ways. The model is misspecified. This little model I showed you right here certainly does not describe influenza transmission dynamics in Seattle. It's highly misspecified. It assumes everybody's in the same room with each other. It doesn't say anything about differences there. Very simplistic model, okay? So we have model misspecification as a problem. We also don't know what the parameters in this model should be or the initial conditions are. And given that, all those errors compounded in it are going to amplify over time if we don't do something about it. So if we were to run this model in free simulation, and the black here is the true outcome, we might make some simulation or forecast that looks like that red epidemic curve right there. And that's a terrible forecast, clearly. It's gotten everything wrong that you would want to get right. If you were to imagine that these are weak markings right here, so these are weekly markings, In particular, if you made this forecast here, let's say at week 15 right there, that's really not something you'd want to do. You want the model to be informed that over the last 5-6 weeks, there has been an uptick in influenza activity. You want it to recognize that, and you want it to conform its inner state space, the state space of the model, and its parameters to position it so that it's capable of actually emulating the outbreak as it has thus far been observed. The idea being that if you can make it and train this model so it can actually represent what's thus far been observed, it will have a better chance of forecasting what will, in fact, manifest in the future. So that's the name of the game. What we do is we train our model in real time, iteratively, with each new observation that comes in over time, using data assimilation methods, and this adjusts and optimizes the model. The idea is that, again, if we can train that model to represent what we've seen thus far, maybe it's Seattle in the 2017-18 season, we're going to have a better starting point for doing that. And we're going to be able to not only optimize the observed variable, influenza incidence, but we can use these data assimilation methods to adjust everything else within the model structure. And they have a variety of ways of doing that. It's all part of their algorithms. The end result is that we want to make an ensemble of forecasts, okay? A plume of forecasts that we're going to send the model into the future. Once we've taken the very last observation that we have in hand, we then run the model without further optimization, because we have nothing else, into the future to generate a forecast. And that forecast gives us a spread, a probabilistic reach into the future to tell us what might happen. So here's an example. We started doing this operationally in the 2012-13 season. This is a real-time forecast that we generated for Salt Lake City around the middle of December of 2012. I'm showing you a good one. There are good ones and there are bad ones, and that's part of what we evaluate, and we're trying to make it so that we get more good ones than bad ones and improve it over time. If you look at this, what you're seeing here are the black X's are observations of influenza incidence, ILI plus, for Salt Lake City that we had in hand at the time. From weeks 40 through week 50 are shown there, but we actually had going further back in time. The blue line is what's called the mean posterior. It's the adjustment of the model to an optimized state. It's actually not one realization there, but that's 150 200-member ensembles overlaid there. We run different ensembles because we want to see what the stochastic effects of different initiation have on the forecast outcome. Now, the red X's are observations that we did not have in hand at time, but were what actually manifest ultimately. Obviously, this is now in the past. The gray lines are the means of each of those 200-member ensembles. So there are 150 of them there. What you can see from this is that we're getting the overall attack rate. We're getting the duration of the outbreak correctly. We're predicting that the peak will be in 5 weeks in the future. And that peak up there is a little high, but I'll show you from a statistical point of view that's actually quite fine. We did actually pretty well with that as well. Now, when we generate these forecasts, we don't want to just say, let's say, that influenza is going to peak in 5 weeks in Salt Lake City. We would really like to give more information than that. And that gets to the idea of a calibrated forecast, okay? I used to teach at Oregon State University, and I would teach weather and meteorology there, and I once gave an example, and I was trying to explain to them what it means to have an 80% chance of precipitation. And I said, when there's an 80% chance of precipitation, how many of you take an umbrella? And none of them raised their hands. It was a class of 50 of them. And I'm sitting there scratching my head and going, really? What? Huh? And then one of the kids raised his hand and said, well, I might wear a rain jacket. And I go, well, how many of you would wear rain jackets? And they all raised their hands. So I got to be careful what the audience I'm talking to, and I'm back in the Pacific Northwest right now. So the idea here, using the umbrella analogy again, is that when we get a local weather forecast, they'll tell us it's not, they don't say it's going to rain tomorrow or it's not going to rain tomorrow. They say there's an 80% chance of rain tomorrow or a 20% chance of rain tomorrow. And we're familiar with those enough that we intuit our own way of responding to it, whether we take an umbrella or not. I will take an umbrella if there's an 80% chance of rain. I will not, most likely, if there's a 20% chance of rain. We want to be able to do the same thing with our flu forecasts. We don't want to just say that flu is going to peak 5 weeks in the future. We want to say there's a 70% chance flu will peak in 5 weeks in the future. And we can contrast that with another forecast that might say there's a 15% chance that flu will peak 5 weeks in the future. Both of them, through the ensemble, are predicting the same most likely outcome, but there is much greater certainty associated with the former forecast rather than the latter. And if we can deliver that information, that embeds that uncertainty information into something that might be actionable in one instance versus a wait and see in the other. And the way we get at this is that I'm going to pull apart one of these gray lines now and show you the spaghetti that underlies the 200-member ensemble in this case. So what you see is that there is a lot of disagreement within this, but it's not nearly as bad as it is in many, many cases. This is actually a reasonable amount of convergence. One of the things that's very nice statistically is that credible interval that's spanned by that green goop actually spans that observation that's way up high there, which is very good. And we can actually use the disagreement within this ensemble to make an estimate of how certain we are in this forecast. So the disagreement of those different trajectories tell us that certainty. If they're tighter, if they're more bunched, we're going to see an increase in the likelihood that a forecast is correct. Whereas if they're not, they're not. We can make that calibrated forecast, and we're working towards it, not as well as the National Weather Service does at this point, but something along those lines. We want to be right 70% of the time when we say there's a 70% chance of something happening. And we want to be right 20% of the time when we say there's a 20% chance of something happening. So we first did this, as I mentioned, in the 2012-13 season. We did it in real time for 108 cities in the United States. We wanted to verify a number of issues: the accuracy of the forecasts, are they superior to some climatological expectants, whether or not the expected accuracy, which is that calibration I was just talking about, plays out. Does it suggest that we're going in the right direction? And we wanted to know, how far in the future are we able to forecast events? I showed you one that says we can forecast something 5 weeks in the future, which is a lot farther in the future than you get for numerical weather prediction, which has to do with the fact that numerical weather prediction is a more nonlinear or chaotic system than the ones we're dealing with here. All right, so what you're seeing here is a plot showing you the fraction of forecasts that were accurate over time. It shows you for a 12-week period starting from about mid-November of 2012, over all 108 cities until middle of February, week 6 of 2013. What you can see is that by week 52, the last week of December, 63% of the forecasts for the 108 cities were accurate, within some margin for peak week, okay? And 84% of cities actually peaked. They had their peak at week 2 or later. So we were well in advance of what was happening. We were able to make forecasts with some reasonable lead. And you can see we trailed up. We got up to more than 75% accuracy for that season. All right? Another thing that we did, and this is a measure, it's a little difficult to follow, so I may run through it pretty quickly here, but we're looking at this measure of these calibrated forecasts. What you're seeing here is that level of disagreement, that ensemble spread, that allows us to say the percentage or the likelihood that something will happen, the expected accuracy of it. And what you can see from these red lines is what we found looking at it, retrospective or historical forecasts. And what we see with the red line is that as you get to a tighter variance, you get an increase in the certainty that the prediction is correct. For predictions saying something's 1 to 3 weeks in the future, 4 to 6 weeks in the future, and then 7 to 9 weeks in the future. The blue line shows you how well the forecasts actually did, the fraction that were likely for a given week into the future, given the ensemble spread, how well they did. You can see there's good match at 4 to 6 weeks. We're kind of bobbing around the same line. That's the red line there. And then for 7 to 9 weeks, for which there weren't that many, we got very lucky and did very well. But over time, if I add more and more of these seasons on, we really do converge to these lines, and they become stronger, and we're able to make this calibrated forecast. The other thing is that we had forecast leads of up to 9 weeks, and those have gone even further in some instances for influenza. Well, this was the core system that we started with when we built it, but there's a lot of work that remains to be done. We want to see if we can build better model forms, look at stochastic versus deterministic effects, get down to specific strains or at least types and subtypes of flu, different types of diseases. Can we do something that's spatially explicit? Can we improve the model optimization and the data assimilation methods? And can we provide forecasts for local public health decision use? So I'm going to just zip through a few things, but before I do that, I'm going to show you this thing that I took off the National Center for Environmental Prediction, which is part of NOAA website. What it shows you is a history over the last 60 years, roughly, almost to the present, of how well numerical weather forecasts have done at predicting a field, which is just the 500 millibar field is just halfway up the atmosphere over North America at 36 and 72-hour forecast leads. This is just some measure of skill, which is increasing relative to some baseline that they compare it to. And it starts from the very beginning of numerical weather prediction in 1955 there. And what you can see is there's basically a monotonic increase in the skill of forecasting at both 36 and then 72 hours as they go farther out. These forecasts have gotten a lot better over time. And the reason they have is because there's been a lot of investment in it. It's been investment in improving the models and understanding the physics and sometimes even the chemistry that needs to go into them. In the computational speed, they've invested in computer infrastructure. Weather models are very computationally expensive. As they get bigger and bigger, they can do them at smaller and smaller, finer and finer resolution, and they can resolve processes that they weren't able to before. It also, this is what this shows you. This shows you different computing systems that were brought online. It also benefits from improvement in the data assimilation methods. Those have come on board. And most importantly, I would argue, even the observations. So the network of observations has improved over time. Particular satellite observations were not available at this time when they started. They really came into full bloom in the late 70s. Can't predict a hurricane if you don't know that there's the seeds of the storm over the tropical Atlantic. It's that kind of information that's very, very important and has allowed the continued improvement. And my argument here is that we need the same thing for infectious disease. We need to improve our ability, our understanding of the processes there, our ability to represent it well, our observations of their system, think creative ways of thinking about data assimilation, and we're using methods that are out there and developing some of our own that are specific for the context in which we use them. All right, so what have we done? We've done comparisons of various filtering methods to look at what that does. Because I'm a little low on time, I'm going to whip through some of this. One of the things we invented something new, developed basically this idea of space reprobing, which allows us for both particle filters and Kalman filters to actually reprobe the state space in case so we don't get too much convergence, or as it's called in the case of the ensemble filter, filter divergence. We've taken it to subtropical locations where we have data streams to work with, and we've developed flu forecasts by type and subtype. We've also done this in the US, and we found that if we go beyond ILI plus to A plus specific, or B, or even H3N2, or just H1N1, we make more accurate forecasts using those individual types or subtypes rather than some aggregate ILI plus. And that's because the model is representing it as a single disease. So if we can pare it down to a single disease, we're going to get better estimates. In fact, we can make a better forecast if we go by type and subtype and then just add those forecasts together. That produces a better forecast than doing ILI plus in aggregate. We've also looked at how we do this forecast calibration. Are there ways of actually improving that? And we found something we call streak that allows us to actually put more confidence in certain forecasts when we see that over successive weeks we're getting the same target matched. We also looked at that thing that I told you was in there. We actually have humidity forcing in our model because influenza transmissibility and survival seems to be modulated by the levels of absolute humidity in the ambient air. And we put that in as a forcing agent within our models, and we wanted to test this. And when we take it out, you can see for the no humidity forcing right there, this is a ranking of 3 different versions of humidity forcing and a no humidity forcing. And you can see that the no humidity forcing is usually ranked 4th or worst in terms of its pairwise comparison for how well it's doing. We've also used purely statistical approaches. There are a number of Bayesian approaches that we can do, Bayesian weighted averaging of a sort using historical forecasts, historical outbreaks. It's an analog method we can use to generate forecasts. And then we also have done some more recent work where we've looked at this idea of a super ensemble. All of our forecasts are probabilistic and they're ensembles of the future. We're looking to validate them, but there's an issue where when you have 2 different models and they're giving you competing forecast outcomes, how do you reconcile them? How do you know which one to trust? How do you figure out what to use best? Turns out something that they've done a lot in weather and climate forecasting. They've found actually if you just take a straight average of forecast models, different models, does better than any one individual model. Basically, the individual biases of the models offset one another, or offset through the averaging process. You can also develop weighted averaging using a number of Bayesian methods, and that actually can improve the forecast even further. And this is something that we've applied to our influenza forecast, and this just shows you 21 different models that we run that we put into a weighting scheme for the timing of the peak and the number of cases at the peak, and you can just see some of the weights that were assigned to them. And this is how we would generate a super ensemble that would reconcile those competing forecasts. Another thing that we look at in my group is we've been looking a lot at the dynamics within the model we use. We're using a dynamic model. It's process-based. It's described mathematically. And the dynamics are nonlinear. And within nonlinear dynamical systems, there's all sorts of issues associated with error growth that have been documented in some other fields. And we've been applying that to the SIRS model to have a better understanding of what's going on, how error explodes within the model, and then trying to use that to counteract it and actually improve our forecast. So if we can counter this nonlinear error growth in the model, particularly when we're in the area where we're in the meat of the outbreak, the main portion of the outbreak, we can actually do an additional correction more than just what the data assimilation models do, which is a state space linear correction, really. And we actually get something that anticipates the nonlinear growth, backs it out, and adjusts the model and allows for an even better forecast, we found. Now, we don't just look at flu. We've looked at a number of other diseases, including respiratory syncytial virus, West Nile virus, dengue, and Ebola. And I'll just show you a couple of examples here. So West Nile virus is something that we've begun doing. We even did it a little bit operationally this past year in 2017. We'll probably do it again in 2018. In this one, we have multiple data streams that we can bring to bear. We have both human case counts of West Nile virus, and we also have mosquito infection rates. So those mosquito infection rates we can get from mosquito abatement districts and control districts, and there's select places where they get this, and it's available close enough in real time that we might be able to actually generate forecasts. So this is showing a combined model system that has both zoonotic transmission between birds and mosquitoes as well as spillover to humans. And what we find is we don't get great lead when it comes to predicting mosquito infection rates, which are very noisy data. However, the constraint that we get within the model allows some really fairly good predictions of human case levels. 9, 10 weeks in advance of the end of the season, we're able to predict, in many cases, the number of human cases you're going to see in a given county. So we're exploring how to operationalize this. There are some real issues associated with it. For instance, there are enormous delays in when human cases get reported in real time, delays of 2 up to 12 weeks. So if there's a 12-week delay in when a human case is reported, we're past the end of the season, and that can be problematic. We also did this in Africa. For West Africa during the Ebola outbreak, we generated some forecasts. We developed a number of different models, tested them out, and generated some epidemiological forecasts, particularly during the exponential growth period during that outbreak. We've used the same methods, which is a model inference framework, to try to infer the spatial spread of it purely based off of epidemiological information. And it's something that actually we think could be applied in real time. If you were to have another outbreak of this nature or another type of outbreak, we're able to identify and infer likely sources of infection and where there might be windows of opportunity for shutting off or focusing intervention efforts. We've also looked at spatial temporal forecast of flu. And we've done this at a couple scales. One is within New York City, where we broke it apart into its 42 neighborhoods that are designated there, each of which is about 200,000 people, so it's like a mid-sized city. And we've actually looked at that to see whether we can use commuting patterns and develop something that would tell us about the movement and spread, because there's actually quite a bit of heterogeneity within New York City at the neighborhood level in terms of ED visits for influenza. And then we took a large-scale data set from the Department of Defense with over 60 million patient line records in it, and we applied it to 35 states for which there were data. And we put in a commuter system and a random movement system, and it's a whole metapopulation framework. And at that point, it becomes a much larger system, but we were looking at this and saying whether or not we could do a couple things. Is it going to improve the forecast over forecasts generated in isolation for each state? And is it going to allow us to predict the arrival of the pathogen in a location? Now, we're not hoping to predict the very first case of flu, but we're looking to be able to predict when flu is going to materially lift out of the noise. Can we predict that point in time well? And what we found is the blue are this metapopulation network model, and the red, orangish are the forecasts done in isolation, that our ability to predict was actually significantly improved, particularly for this onset that I just referred to. So this is something that we're finding very encouraging, because actually putting something into a large spatial temporal structure seems to actually reap benefits. And one other thing I just want to point out about this is not only does it do that, but the biases in the model are greatly improved. So if you look at the blue here, the blue shows you the scatter of observations within the credible intervals, and actually just the bias of the observations for different lead predictions right there. And what you can see for the blue, which is the network model, is it's more normally distributed, which is what we want the error to be, and the error, which are these numbers right there, is reduced compared to the models in isolation, which have much more of a skewed structure to them, and the mean bias is much greater. So statistically, this is improving things well with our probabilistic forecasts too. So we do this in real time on an operational portal we've had open for the last 5 years, generating forecasts at both the city and state level in the United States. We do it for ILI plus as well as type A and type B in isolation. Example forecast showing you right here. It's actually a number of weeks of forecast shown for Boston right there. And what are you going to do with this? What do you do with this kind of forecast information? Well, I think there are a lot of uses for it potentially. I think for the general public, there's no reason why we shouldn't have a nightly flu forecast. They already give us pollen levels and pollution counts and sometimes even forecast it. So why not a forecast of the pathogens? This is enough lead time with this so that people are advised. They may go out and be encouraged to get vaccinated. They'll still have time before the peak in this instance for the adaptive immune response and antibody production. Also just for general awareness of circulating germs. Now, for public health officials and clinicians, I think there are more uses. Certainly, we have a big country, and the distribution of vaccine and antivirals to regions of more urgent need can be better planned and managed this way. We can also inform school closure decisions, hospital resource staff management. This year, New York City had to put up temporary tents to handle all the overflow. They enacted or they mobilized the Reserve Medical Corps. So things of that nature really could be dealt with. One of the last things I'm going to just point out is, real question is, are these forecasts being utilized? We have to integrate it into decision making. We have to integrate it into sensible decision making using this uncertain information, the same way we would want to use observations to inform situational awareness in an informed sense. So my last slide, conclusions, accurate infectious disease forecasts can be generated. If we invest in them, we can improve them, and I think there are a lot of uses that we could find for them. I lied. I also have to talk about my funders, and I'm going to acknowledge all my colleagues who have been involved in this as well. Thank you.
So let's take 2 questions for Jeff. Yeah, please.
Hi, I really got knocked out by this flu. I was out for a full week and then 3 weeks to recover. So I started looking into, and I did look a little at your website and several others. Mm-hmm. I'm told that one of the problems with the severity is they missed the H3N2 species of the flu, and you said you were much better on the diagnosis of the individual strains of the flu, and that miss meant with the timing of production of vaccine that the vaccine was off. Did they believe your projection? Was your projection on the strains correct?
Well, that's the difference between the type of forecasting that we're doing. So our forecasting is done within season.
I did hear that, yeah.
Yeah, so it's not going to start till October. They make the decision on what they're going to include in the vaccine in February. They've already made the decision for next year, and it's not informed by what we're doing here. So this is really about situational awareness and what's happening once the outbreak has started. Yeah.
I did talk to Carnegie Mellon. They said that there had been discussions of future forecasting of strains, but they'd never been implemented. Are you aware of those? Is that a funding problem or a possibility problem?
This is Roni Rosenfeld and his group there?
Yeah, David Farrow in particular.
Yeah, so again, what they're talking about is the type of strain-specific forecast that I'm talking about here. It's not going to be something, well, don't point me going back like this. It's not going to be something that's actually going to be predicting year-to-year differences. In other words, there was a lot of talk in the popular media this year that Australia had it really bad, very severe strain of H3N2, and that we could potentially be in for something really bad. Now, H3N2 tends to produce more severe symptoms. It's more virulent, and the vaccine effectiveness, last time I saw the estimates, about 30%. Is that right, Trevor? And so, you know, it wasn't as effective as you'd want it to be. I think in ferrets, it was a pretty good match, though, right? It was the egg adaptation. So they cultivate it and they culture it in eggs. And during that time, it drifts, it mutates. So that's part of the problem with the production process that's underway. So when you're talking to David Farrow or Roni Rosenfeld and such, they're talking about the same kind of forecast I am. It's not about prediction for the flu strain and what's going to happen in a year. Different time scales.
In the literature that's popping out on the web, I've begun seeing discussions of mixing what was historically called genetic algorithms with the AI methods of doing this. And in my imagination, that was a way to keep up with the mutation of those strains. Have you seen anything about?
You're talking about genetic algorithms within the whole thing? Is that what you're referring to?
Yeah.
Well, you know, the idea of trying to, within season, integrate genomic information, sequence information into it, and use the fact that there may be drift or antigenic advancement into these models is something we're looking into. I pointed to Trevor, but Trevor and I have been talking about this, and we're working on this right now. And the question is whether or not that's something that let's say theoretically, retrospectively, if you have perfect information, will actually improve the forecast. That's the first step towards it. And then the second question will be whether or not you're going to get the information in a timely enough manner, which I think you probably could, so that you could inform and improve a forecast that way. Yeah. I mean, those are the types of improvements that are going to lead to an improvement in the forecast. It's going to be continued incremental improvement.
Yeah. Thank you.
Yeah.
Okay, thank you. Let's thank Jeff again.
You're welcome.